Module 19, Lecture A, Output Structures. By the end of this lecture, you will be able to apply multi-class strategies for estimators that need decomposition wrappers, model multilabel and multi-output classification targets in Scikit-Learn, and use chained estimators for dependent classification or regression outputs. Multi-class strategies. Native multi-class support. Native multi-class support means a model can handle 3 or more exclusive classes directly, instead of turning the task into multiple binary comparisons. This lets the estimator learn from all class labels at once, which simplifies modeling and uses the available class information more efficiently. Native multi-class support lets a classifier learn all class labels at once, so you can fit the model directly to a multi-class target. In Scikit-Learn, many classifiers handle this internally, either by separating the feature space into class regions or by estimating class probabilities. This reduces the need for manual decomposition methods and makes multi-class modeling simpler. Native multi-class support is useful, but you still need to check whether the estimator fits the problem. These models work best when classes are clearly separated and the training data represents them well. In real data, some classes may be rare or overlap with others, which can hurt accuracy. Always evaluate performance for each class, especially less frequent ones. Python code. Native multi-class support. This example shows native support for multi-class classification by training one estimator directly on the 3 iris classes. Its predictions are then compared with the true iris labels to evaluate how well it classifies each sample. We import key tools from Scikit-Learn to build and evaluate a simple classification model. The iris dataset loader provides flower measurement data. The train test split function separates it into training and testing sets. And the DecisionTreeClassifier creates the model. Finally, the accuracy score function measures how well the model's predictions match the true labels. We load the iris dataset from Scikit-Learn, a standard dataset for classification. It contains flower measurements, such as petal and sepal dimensions, along with labels for 3 flower types. These features and labels provide the data needed to train and evaluate a classification model. The code checks how many flower classes are in the iris dataset by counting the target names. It then verifies that at least 3 classes are available, since the example is meant to demonstrate multi-class classification. If fewer than 3 classes are found, it raises an error to show the dataset is not suitable for this task. We split the data into training and testing sets using Scikit-Learn's train test split function. 30% of the data is reserved for testing, while stratification keeps the class proportions consistent in both sets. A fixed random state makes the split reproducible, and the result is separate feature and label data for training and testing. We build a DecisionTreeClassifier in Scikit-Learn with a maximum depth of 3 to keep the model simple, and a fixed random state for reproducible results. After training it on the feature data and target labels, the tree learns patterns that let it classify new samples into one of the 3 flower classes directly. The DecisionTreeClassifier predicts a class label for each test sample using the patterns it learned during training. Its accuracy is then measured by comparing those predictions with the true labels, showing the proportion of test samples classified correctly. The output first confirms the Scikit-Learn version, then shows how many iris classes the model learned and names those classes. It reports the test accuracy rounded to 3 decimal places as a quick performance measure. Finally, it compares the first 8 true test labels with the model's first 8 predictions to give a brief check of how well the predictions match the actual results. This script shows how Scikit-Learn handles multi-class classification directly with a decision tree. It uses the iris dataset, splits it into balanced training and test sets, trains a shallow tree, and predicts the 3 flower classes. It then reports accuracy and basic model details, including the learned classes and a small comparison of true versus predicted labels. 1 versus rest. 1 versus rest turns a multi-class classification task into several binary tasks. Each classifier learns to recognize one class against all others, such as sports versus non-sports or finance versus non-finance. At prediction time, all classifiers evaluate the same example, and the class with the strongest positive response is chosen. This approach is useful when the underlying model is designed for binary classification. The 1 versus rest approach is a simple and efficient way to handle multi-class classification by training one binary classifier for each class. Each classifier learns to recognize its own class against all others, which makes the method easier to manage than training classifiers for every pair of classes. In Scikit-Learn, it is commonly used to apply binary algorithms to multi-class problems, such as identifying one medical condition at a time in a triage system. In a 1 versus rest approach, each binary classifier separates one class from all the others, which can create class imbalance, especially for rare classes. Final prediction depends on comparing the classifier's confidence scores, so performance relies on how meaningful those scores are. Even with these challenges, 1 versus rest remains a common way to use binary classifiers for multi-class problems. Python code 1 versus rest. This demonstration shows how 1 versus rest classification extends a binary logistic model to handle multiple iris classes. The model trains separate binary classifiers for each class, then compares their scores for a test flower. The class with the strongest score is selected as the prediction. We import key Scikit-Learn tools to build and evaluate a classification model using the iris dataset. LogisticRegression is used as the classifier, with accuracy score for evaluation and train test split to separate training and testing data. For multi-class classification, the 1 versus rest approach turns the task into several binary problems. A pipeline combines feature standardization with the classifier, helping the model work more effectively. We load the iris dataset from Scikit-Learn as a standard example for multi-class classification. Its flower measurements are used as the input features, and the species labels are used as the targets. This prepares the data for training and evaluating a classification model. The code verifies that the target data contains exactly 3 unique iris classes. If it does not, it raises an error explaining that 3 classes are required. This check confirms the dataset is appropriate for the intended multi-class classification task. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function, with 30% reserved for testing. Stratification keeps the class proportions the same in both sets, supporting fair model evaluation. A random state of 42 makes the split reproducible. We build a multi-class classification pipeline using LogisticRegression as the base binary model. The features are first standardized, so they are on a comparable scale. Then, a 1 versus rest strategy trains one binary classifier for each class. The model also uses a fixed random state for reproducibility and allows up to 300 training iterations. We train the model on the training data using a 1 versus rest approach, where a separate binary logistic regression model learns to identify each class against all others. Once trained, these models are applied to the test data to produce a predicted class label for each test example. The model computes decision scores for the first test sample, showing how strongly each 1 versus rest classifier supports its class. These raw scores are then matched with the iris class names and rounded for readability, giving a compact summary of how the sample was evaluated across all classes. The output summarizes a 1 versus rest classification run on the iris dataset. It reports the Scikit-Learn version for reproducibility, the number of binary classifiers trained, and the model's test accuracy. It also shows the decision scores for one test sample, indicating each classifier's confidence, and then gives the predicted iris class name for that sample. This script shows how one versus rest classification can handle the multi-class iris dataset. It splits the data while preserving class balance, trains logistic regression as separate binary classifiers for each class, and evaluates the model on test data. It reports the Scikit-Learn version, the number of classifiers, and the test accuracy, then shows the decision scores and predicted class for one flower. The main idea is that a multi-class problem can be broken into simpler binary comparisons. 1 versus 1. The 1 versus 1 strategy turns a multi-class classification problem into several binary tasks by training one classifier for each pair of classes. At prediction time, each classifier votes for one of its two classes, and the class with the most votes is chosen. This is useful when a binary estimator cannot handle multi-class targets directly, because it extends the estimator without changing its learning algorithm. 1 versus 1 classification trains separate models for each pair of classes, so each classifier focuses only on the boundary between two categories. This can help distinguish classes that are very similar or easily confused. While the method may require many pairwise classifiers as the number of classes grows, each individual model stays relatively simple and can capture subtle differences effectively. In Scikit-Learn, the 1 versus 1 strategy handles multi-class classification by training binary classifiers for each pair of classes. It can work well when class boundaries are complex or when the estimator is strong on binary problems. Because the final prediction combines many pairwise decisions, mistakes in those comparisons can influence the result. Evaluate carefully, since overall accuracy may hide problems such as one class repeatedly losing votes. Python code 1 versus 1. This section demonstrates 1 versus 1 multi-class classification, where pairwise classifiers each vote for a final class. It also compares the wrapper size with test accuracy to evaluate the approach. We import key Scikit-Learn tools for a multi-class classification workflow. The iris dataset provides the data. Train test split divides it into training and testing sets. And a 1 versus 1 classifier uses logistic regression to compare pairs of classes. Finally, accuracy score measures how well the model's predictions match the true labels. We load the built-in iris dataset, a common example for machine learning. It contains plant measurements as features and class labels for 3 iris species, making it a simple dataset for multi-class classification. First, confirm that the dataset contains exactly 3 unique class labels. This check is needed because the example demonstrates a 3-class, 1 versus 1 classification setup. If the target labels do not form 3 distinct classes, an error is raised to show that the dataset does not meet the example's requirements. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function, with 30% reserved for testing. Stratification keeps the class proportions consistent in both sets, and a random state of 42 makes the split reproducible each time the code runs. A logistic regression model is created as the base classifier, with settings chosen for reliable training and reproducible results. It is then wrapped in a 1 versus 1 classifier, which trains separate binary models for each pair of classes. Finally, the combined model is fitted to the training data, so it can learn how to distinguish between the classes. To check a 1 versus 1 model, first count the unique classes it handles, then count the fitted binary classifiers. The expected number of classifiers is found by taking the number of classes times 1 less than that number, divided by 2. This matches the idea that the model trains one classifier for every possible pair of classes. The 1 versus 1 model predicts test classes by combining votes from its pairwise classifiers. We then compare these predictions with the true test labels to calculate accuracy, showing how well the voting approach performs on unseen data. The output checks the Scikit-Learn version for reproducibility, then reports how many classes are in the dataset and how many 1 versus 1 pairwise classifiers were created. It confirms this count against the expected number based on all class pairs, then shows the model's test accuracy on unseen data. Finally, it displays the first 5 predicted class names to give a quick view of the model's results. This script shows 1 versus 1 multi-class classification on the iris dataset using logistic regression with Scikit-Learn. The data is split into training and test sets while preserving class proportions, and the model trains 1 binary classifier for each pair of classes, giving 3 classifiers for the 3 iris classes. It then predicts the test data and reports key results, including the Scikit-Learn version, class and classifier counts, test accuracy, and the first 5 predicted class names. Overall, it demonstrates how pairwise voting supports multi-class classification. Multilabel outputs. Multilabel classification. In multilabel classification, one example can have several labels at the same time, rather than choosing just one class. Each label is treated as a separate yes or no decision, such as a news article being marked for politics, economics, and international affairs. In Scikit-Learn, these labels are stored in a 2-dimensional indicator format, with samples as rows and possible labels as columns. In Scikit-Learn, multi-label classification can be handled with binary relevance, which turns each label into its own binary prediction task. This lets you use standard classifiers to predict labels such as beach, people, or sunset, then combine the results. The key limitation is that it treats labels as independent, even when real-world labels may be related, such as beach and ocean. Evaluating multi-label classification is harder than single-label classification because a prediction can be partly right. Metrics may emphasize matching the entire label set, finding most relevant labels, or avoiding wrong ones, depending on the task. In Scikit-Learn, choose evaluation measures that reflect the real cost of errors and account for label imbalance, especially when some labels are much rarer than others. Python code, multi-label classification. This demonstrates multi-label classification using indicator targets, where each sample can belong to more than one label. The results show both partial correctness, when some labels are predicted correctly, and exact correctness, when the full label set matches. We import NumPy for numerical work and Scikit-Learn for machine learning tools. From Scikit-Learn, we use the multi-label classification dataset generator to create synthetic data, and the train test split function to divide it into training and testing sets for evaluating performance on unseen data. We import tools from Scikit-Learn to build and evaluate a multi-label classifier. The 1 versus rest classifier trains a separate binary model for each label, using LogisticRegression as the base model. We then use accuracy to measure exact label matches and the micro-averaged F1 score to summarize the balance between precision and recall across all labels. We create a small multi-label dataset using the make multi-label classification function to simulate data points that can belong to more than one category. The dataset has 300 samples, 8 features, and 3 possible labels, with each sample assigned about 2 labels on average. A fixed random state ensures the results are reproducible. The code validates that the labels are in the right shape for multi-label classification. It checks if they form a 2-dimensional indicator matrix with exactly 3 columns, 1 for each possible label. If the shape is incorrect, it raises an error, so the data is fixed before model processing. We split the dataset into training and testing sets using Scikit-Learn's train test split function. The features and labels are divided together so they stay aligned, with 25% of the data reserved for testing. Setting the random state to 42 makes the split reproducible each time the code runs. A logistic regression model is set up with a fixed random state and a limit on training iterations to ensure reliable results. It is used inside a one versus rest classifier, which trains a separate binary model for each label in the multilabel dataset. After fitting the model to the training features and labels, it learns patterns for each label, so it can predict labels for new data. To evaluate the model, we first use its predict method to generate labels for the test samples. We then compare these predictions with the true labels using exact match accuracy, which counts only samples where every label is correct. Finally, we calculate the micro F1 score to summarize overall precision and recall across all label categories. Define the label names, such as sports, finance, and health, so numerical model outputs can be read as meaningful categories. For the first test sample, convert both the true labels and the predicted labels into Boolean selections. Then use those selections to retrieve the matching label names. This makes it easy to compare what the sample actually belongs to with what the model predicted. The output checks the Scikit-Learn version and the label array shape to support reproducibility and confirm the dataset dimensions. It then compares the true and predicted labels for the first test sample in readable form. Finally, it reports exact match accuracy and the micro F1 score to summarize how well the multilabel model performs overall. This script shows how to perform multilabel classification when each sample can belong to more than one of three labels. It creates synthetic data, trains a logistic regression model with a one versus rest approach, and predicts labels on a test set. Performance is summarized with exact match accuracy, which requires every predicted label to match, and the micro F1 score, which combines precision and recall across all labels. The printed results include basic dataset and prediction checks, along with these final performance scores. Multi-output classification. Multi-output classification means predicting several classification targets for each example, rather than choosing just one class. Each target is a separate but related decision, such as judging both medical urgency and the right referral department. In Scikit-Learn, the targets are stored in a two-dimensional structure where rows represent samples and columns represent different outputs. And each output can use its own set of class labels. Multi-output classification uses the same input features to predict several different targets, often by training a separate classifier for each output. This is useful when each target describes a different aspect of the same item, such as setting, quality, or content type and image moderation. Scikit-Learn supports this approach by adapting standard classifiers to handle multiple outputs. Multi-output and multi-label classification are related but different. Multi-label classification predicts which labels from one shared set apply, while multi-output classification predicts several separate categorical outcomes from the same input. This difference affects how data is prepared, how predictions are interpreted, and how models are evaluated. Performance should be checked for each output as well as overall, because some outputs may be much more accurate than others. Python code. Multi-output classification. This example shows multi-output classification using separate target columns, where each output answers a different categorical question. Performance is evaluated both for each individual output and by exact match accuracy across all outputs. We import NumPy for numerical work with arrays, and use Scikit-Learn for machine learning tasks. From Scikit-Learn, we use the make classification function to create a synthetic classification dataset with features and labels. We also use the train test split function to divide the data into training and testing sets so the model can be evaluated on unseen data. We import three key tools from Scikit-Learn: a multi-output classifier to handle several target outputs at once, a DecisionTreeClassifier to serve as the base model, and an accuracy scoring tool to compare predictions with the true values and evaluate performance. We generate a reproducible synthetic classification dataset using Scikit-Learn. It contains 600 samples with 6 shared input features, 4 of which are informative for predicting the target. The target, urgency, has 3 classes and will support multiple output prediction tasks. 2 binary classification targets are created from the feature data. The department target is set to 1 when the combined values of the first 2 features are greater than 0, and 0 otherwise. The quality target is set to 1 when the third feature is above its median value, and 0 otherwise. Together, these targets split the data into simple categories for classification. The separate target arrays are combined into one 2-dimensional target matrix using NumPy's column stacking function. This lets the model learn to predict urgency, department, and quality at the same time. Each output column is then given a clear name, making it easier to evaluate the model's performance for each prediction task. Before training, the code checks that the target data has the right shape for multi-output learning. It must be 2-dimensional with exactly 3 columns. If not, it raises an error, helping prevent training problems caused by an incompatible data structure. We split the dataset into training and testing portions using Scikit-Learn's train-test-split function. The features and labels are divided so that 25% of the data is kept for testing, while a fixed random state makes the split reproducible. This gives separate feature and target sets for training and testing, allowing the model to learn from one part of the data and be evaluated on unseen data. A decision tree with limited depth and a fixed random state is used as the base model for each target output. Wrapping it in a multi-output classifier lets the model learn several target variables at the same time. After training on the feature data and the multidimensional targets, it can predict all outputs from the input features. We use the model to predict outputs for the test data, including all target columns. Then we measure exact match accuracy by checking whether every predicted output matches the true outputs for each sample. Taking the average of these matches gives one accuracy score, showing how often the model got the full set of outputs correct. We first check the Scikit-Learn version to support compatibility and reproducible results. Then, we inspect the target matrix shape to confirm the number of samples and output columns, ensuring the data is structured correctly for multi-output classification. Evaluate each output target separately by comparing its test values with the model's predictions. This produces an accuracy score for each classification task, which is then reported clearly to show how well the model performs on each output. This line reports exact match accuracy, showing how often the model gets every target output correct for each test sample. The value is rounded to 2 decimal places, giving a brief summary of overall performance across all output tasks. This script shows how to use a decision tree for multi-output classification. It creates synthetic data with 6 features and 3 related targets: urgency, department, and quality. A multi-output classifier trains one model setup to predict all 3 targets at once, then evaluates performance on a test set. The results report accuracy for each target separately, and exact match accuracy for cases where all outputs are predicted correctly together. Classifier chains. Classifier chains help with multi-label prediction when labels are related, such as in news or medical data. Instead of predicting each label independently, the model uses earlier label predictions as additional input for later ones. This lets it capture relationships between labels and can improve accuracy on complex multi-label tasks. In Scikit-Learn, a classifier chain handles multi-label classification by building a sequence of binary models. The first model uses the original features, and later models also use earlier predictions, allowing the chain to capture relationships between labels. This can improve performance when labels are connected, such as in image tagging or customer support categories. In classifier chains, Label order matters because earlier predictions are used to guide later ones. A useful early label can improve the rest of the chain, while an early mistake can spread and reduce accuracy. Since the best order is often unclear, it is common to try different sequences or combine multiple chains. Even with this risk, classifier chains are a practical way to model label dependencies, offering a middle ground between independent labels and modeling every label combination. Python code. Classifier chains. Classifier chains are a multi-label classification method where each label model can use earlier label predictions as additional information. This lets later predictions capture relationships between labels, unlike independent multi-label models that predict each label separately. Comparing the two approaches shows how chaining can improve results when labels are related. We import the main tools needed for a multi-label classification experiment: NumPy for numerical work, and Scikit-Learn for data generation, modeling, evaluation, and splitting the data. The setup uses synthetic multi-label data, LogisticRegression as the base classifier, and the F1 score to measure performance. It also includes train test splitting and compares two multi-label strategies: classifier chains, which model label dependencies, and one versus rest classification. We create a small synthetic multi-label dataset using the make multilabel classification function. It contains 600 samples, each with 10 input features and 3 possible classes, where each sample is linked to about 2 labels on average. A fixed random state makes the dataset reproducible, so the same data is generated each time. This setup provides a simple way to test multi-label classification models with related labels. The code first verifies that the labels data has exactly 3 columns, meaning each sample includes 3 binary labels. If this requirement is not met, it raises an error to stop processing. This check helps prevent later failures because the models expect that specific label structure. We split the dataset into training and testing sets using Scikit-Learn's train test split function. 30% of the data is kept for testing, so the model can be evaluated fairly, and a random state of 42 makes the split reproducible across runs. We use LogisticRegression as the base classifier with fixed settings for reliable training. To handle multi-label classification, we compare 2 approaches: one versus rest, which predicts each label independently, and a classifier chain, which predicts labels in a set order so earlier results can influence later ones. This lets us evaluate whether modeling label dependencies improves performance. The independent model trains a separate logistic regression classifier for each label, treating each one as its own binary task. The chain model also uses logistic regression, but it adds earlier label predictions as inputs when predicting later labels. This lets it capture possible relationships between labels and may improve accuracy. The code compares 2 ways to predict labels on the test data. The independent model predicts each label separately, while the chain model predicts labels in sequence, using earlier predictions to help inform later ones and capture possible label dependencies. We evaluate multi-label predictions using the micro F1 score, which combines true positives, and false negatives across all labels into one overall measure. By computing this score for both the independent model and the classifier chain model, we can compare how well each approach predicts multiple labels at the same time. This example selects one test sample, records the Scikit-Learn version for reproducibility, and defines the 3 target labels being predicted. It then compares the independent model and the classifier chain using their micro F1 scores, rounded for readability. Finally, it shows the true labels for the selected sample alongside the classifier chain's predicted labels, making the results easy to compare. This script compares independent multi-label prediction with classifier chains on a synthetic dataset with 3 related labels. Both methods use logistic regression, and their performance is measured with the micro F1 score across all labels. The key idea is that classifier chains can use earlier label predictions to guide later ones, often producing better results when labels are related. The script also shows one test example to compare the true labels with the model's predictions. Chained regression outputs. Multi-output regression basics. Multi-output regression is used when one input needs several continuous predictions at the same time. Instead of producing a single number, the model outputs a vector of related numeric values, such as multiple lab results, environmental measurements, or costs. This makes the task more complex, because each example has one set of features but multiple targets to predict. In multi-output regression, a simple approach is to train a separate regression model for each target while using the same input data. Many machine learning tools support this directly or through wrappers from multiple regressors. This works best when the outputs are only weakly related or when each target needs dependable independent predictions, such as predicting manufacturing properties like thickness and weight from the same process variables. Basic multi-output regression can predict several continuous targets at once, but it often ignores relationships among those targets. In many real problems, outputs influence each other, such as blood pressure and heart rate, or sales, inventory, and shipping. Chained regression methods address this by using some output predictions as extra inputs for predicting others, helping the model capture dependencies between targets. Python code, multi-output regression basics. This script introduces multi-output regression, where one model predicts multiple continuous target values at the same time. It shows the resulting vector predictions and reports separate errors for each target. This setup imports the main tools needed for a multi-output regression task. NumPy supports numerical work, while Scikit-Learn provides tools to create regression data, split it into training and testing sets, build a multi-output model using linear regression, and evaluate predictions. Model accuracy is measured with mean absolute error, calculated separately for each output. We create a synthetic multi-output regression dataset using Scikit-Learn's makeRegression function. It includes 300 samples with 5 features each, and 3 numeric target values per sample. Noise is added to make the data more realistic, and a fixed random state ensures the same dataset is generated every time. The code first verifies that the target data has exactly 3 columns, because the model is designed to predict 3 values for each input. If the target data does not match the shape, it raises an error before training begins. This check helps ensure the data structure fits the model's requirements. We split the dataset into training and testing parts using the train-test-split function. 25% of the data is held out for testing, and a fixed random state makes the split reproducible. This gives separate feature and target sets for training the model and evaluating it on unseen data. Scikit-Learn's multi-output regressor can predict several target variables by training a separate linear regression model for each one. After it is set up with linear regression and fitted to the training features and targets, it learns the relationship between the inputs and each output, so they can be predicted together. The trained model is used to predict outcomes for the test data. Its prediction method produces a vector for each sample, with one value for each target variable. This matches the multi-output regression setting, where each input is linked to several outputs. Mean absolute error is used to compare the model's predictions with the true target values. By requesting raw values from multiple outputs, we get a separate error for each target. This makes it easier to judge how well the model performs on each output, instead of relying on one combined score. The output checks the Scikit-Learn version for reproducibility. then verifies that the target data and predictions have matching dimensions. It compares the first true target vector with the first predicted vector using rounded values for readability. Finally, it reports the mean absolute error for each of the three outputs, giving a separate measure of how well the model predicts each target variable. This script shows a basic multi-output regression workflow in Scikit-Learn, where one model predicts 3 continuous targets from 5 input features. It splits the data into training and testing sets, then uses linear regression in a multi-output setup, so each target is modeled separately. The output includes the target matrix shape, an example true target vector with its prediction, and the mean absolute error for each target. These separate error values help show how well the model performs on each output. Regressor chains. Regressor chains extend regression to handle multiple continuous outputs by using relationships between the targets. Instead of predicting each output separately, the models are arranged in a sequence, where each later model uses the original features along with earlier predictions. This helps when the outputs depend on one another, because each prediction can provide useful information for the next. A regressor chain makes related predictions in sequence, using earlier predictions to help later ones. This can improve results when the targets depend on each other, such as recovery time, pain, and mobility in healthcare, or temperature, humidity, and air quality in environmental monitoring. The main risk is that mistakes made early in the chain can carry forward and affect later predictions. In regressor chains, the order of outputs matters because earlier predictions become inputs for later models. Use domain knowledge to choose a sensible sequence when possible. And if the best order is uncertain, test several orders and combine their results. Since training uses true target values, but prediction depends on the chain's own earlier outputs, Python code, regressor chains. This section demonstrates regressor chains for predicting related continuous outputs. It compares independent multi-output regression, where each target is predicted separately, with chained regression, where earlier predictions can be used to improve later ones. The key idea is to identify when relationships among outputs make chained predictions more useful than treating each output independently. We import NumPy for numerical work and random number generation, and Scikit-Learn for machine learning tools. From Scikit-Learn, we use linear regression as the base model, mean absolute error to measure prediction accuracy, and a train test split to evaluate performance on unseen data. For multiple target variables, multi-output regression fits one separate model per target, while a regressor chain links models so later predictions can use earlier ones and capture relationships between targets. We create reproducible regression data by using a random number generator with a fixed seed of 42. It generates 500 samples, each with 4 features drawn from a normal distribution. This controlled randomness provides a consistent feature matrix for testing regression models. The targets are generated as a linked sequence. Recovery is based on the first 2 features plus random noise. Pain is then based on recovery and the third feature with more noise. And mobility is based on pain and the fourth feature with additional noise. This creates a chain where each output partly depends on the one before it. We combine the recovery, pain, and mobility targets into one target matrix using NumPy's column stacking function. Each row represents one observation, and each column represents a different target variable. This structure lets a multi-output regression model learn all targets at the same time. Before modeling, the code verifies that the target data has 500 rows and 3 columns, matching the expected samples and 3 regression outputs. If the shape is wrong, it raises an error to stop the process. This check helps ensure the models receive correctly structured data and prevents later modeling problems. The dataset is divided into training and testing sets using Scikit-Learn's train test split function, so both models are evaluated on the same test data. 25% of the data is reserved for testing, and a fixed random state of 42 makes the split reproducible. The split produces separate feature and target sets for training and testing. We build an independent multi-output regression model using Scikit-Learn's MultiOutputRegressor with linear regression as the base model. This approach trains a separate model for each target, so it does not account for relationships between target variables. After fitting it to the training features and outputs, the model learns each input to target relationship independently and is ready to predict new data. A regressor chain is built using linear regression to predict multiple targets in a fixed order. Each target prediction is used to help predict the next one, allowing the model to capture dependencies between targets. The chain is then trained on the feature and target data, so it can learn both feature relationships and target relationships. The code compares two ways to predict multiple target values on the test data. The independent model predicts each target separately, while the chain model uses earlier target predictions to help predict later ones. Comparing their results shows how well each method captures relationships between the targets. We compare the independent model and the chain model by calculating the mean absolute error for each on the test data. This measures the average size of the prediction errors, regardless of direction. The model with the lower mean absolute error is more accurate on unseen data. To show how a regressor chain predicts multiple outputs, we apply the model to the first test example and obtain predicted values for each target variable. The predictions are then rounded to 2 decimal places, making them easier to read and interpret. The output first reports the Scikit-Learn version to support compatibility and reproducibility. It then compares the mean absolute error of an independent multi-output model with a regressor chain model, showing how accurately each predicts the target values. Finally, it prints a rounded example prediction from the regressor chain to illustrate its sequential output predictions. This script compares independent multi-output regression with regressor chains for predicting related continuous targets. The independent model predicts each target separately, while the chain model predicts targets in sequence, so later predictions can use earlier ones. Both models are trained and tested on the same data, then compared using mean absolute error. The main takeaway is that regressor chains can improve accuracy when the target variables depend on one another. Output dependencies. In multi-output regression, the targets often depend on each other, so predicting each one separately can miss useful relationships. Chained regression addresses this by using earlier predictions as inputs for later predictions. This helps the model learn both from the original features and from dependencies among outputs, often improving accuracy. Regressor chains predict multiple targets in sequence, letting each prediction help inform the next. The first model uses the original features, while later models also use earlier predictions, which helps capture relationships between outputs. This is useful when one outcome provides context for another, such as using machine temperature to estimate wear. Output dependencies can improve predictions, but they must be modeled carefully because each prediction can influence the next. A good early prediction may help later ones, while an early mistake can spread through the chain. To reduce this risk, practitioners may test different prediction orders or use multiple chains. Effective chained regression depends on identifying real relationships, not just correlations, using both statistical evidence and domain knowledge. Python code output dependencies. This example compares independent regression with chained regression. It shows that earlier predictions can improve later targets when the targets depend on each other, and the printed scores reveal the effect of using a chain. This setup imports the main tools needed for a multi-output regression workflow. NumPy supports numerical array operations, while Scikit-Learn provides linear regression, model evaluation with the R-squared score, and data splitting for training and testing. It also includes tools for predicting multiple target variables, either by fitting separate models for each output or by using a regressor chain to capture dependencies between outputs. We create a NumPy random number generator with a fixed seed of 42, so the synthetic data is reproducible. This ensures the same random numbers are produced each time the code runs, supporting consistent experiments and easier debugging. We generate a synthetic dataset with 300 observations. Each observation has two input features, created as random values drawn from a normal distribution using NumPy. Random noise is generated with a standard deviation of 0.4 to simulate real-world variation in the data. The target temperature is then calculated from the input features by doubling the first feature, subtracting the second, and adding the noise, creating a realistic target that depends on the features with some randomness. The where target is modeled as partly dependent on the temperature target. To make the data more realistic, random noise with a standard deviation of 0.4 is added. Where is then calculated mainly from temperature, with an additional contribution from the second input feature, capturing a real-world relationship between temperature and where. The target data is combined into one structure for multi-output regression. A column stacking operation joins the temperature target and where target into a two-column array, so each row contains one observation with both target values. This keeps the targets aligned and ready for use in the regression models. This code checks that the target data has the right shape for the model. It confirms that each sample includes two regression outputs and raises an error if that expectation is not met. This validation keeps the data consistent and makes future changes easier to catch. We split the data into training and testing sets so both models are evaluated on the same examples. Using Scikit-Learn's train-test split, 30% of the data is reserved for testing. A fixed random state makes the split reproducible, so results stay consistent across runs. We use Scikit-Learn's MultiOutputRegressor to build a separate linear regression model for each target. After training it on the input features and target values, we predict targets for the test data. This method assumes each target is independent of the others. A regression chain model with linear regression predicts multiple targets in a set order. In this case, it predicts temperature first, then uses that predicted temperature as an added input to predict where. After training on the input features and target values, the model is used on test data to produce predictions for both temperature and where. We evaluate both models by calculating the R-squared score for their where predictions on the test set. This score shows how closely each model's predicted where values match the actual values, with higher scores indicating better performance. Comparing the independent model and the chain model scores tells us which one predicts the where target more accurately. The output first notes the Scikit-Learn version to support reproducibility, then clarifies that temperature is predicted before where. It compares the R-squared scores for where from an independent model and a chained model. The key point is that the chained model may predict where more accurately because it can use earlier predictions as additional input features. This script compares independent and chained regression models on synthetic data with two related targets, temperature and where. The independent approach predicts each target separately, while the chained approach predicts temperature first and uses that prediction to help predict where. By comparing R-squared scores for where, the script typically shows that chaining performs better because it captures the dependency between the targets. In this lecture, you learned to apply multiclass strategies for estimators that need decomposition wrappers, model multilabel and multi-output classification targets in Scikit-Learn, and use chained estimators for dependent classification or regression outputs. In the next lecture, Lecture B, we will go over semi-supervised.
Thank you for your attention. See you all in the next lecture.